Good morning, my name is Daniela Fritz. I study Civil Electronic Engineering at the Universidad La Frontera, and today I will talk to you about continuous volcano seismic monitoring in two steps applied to the Chillan Volcano. The organization of my presentation is as follows. Firstly, I present the motivation of this work. In second place, the Qerlet representation and the hyperbolic secant time-scale transform are presented. After that, convolutional neural network is presented. Following, we introduce the continuum monitoring, where we apply the events classification. Then, the result of application in automatic identification and classification of volcanic seismic events are presented. Finally, the conclusion of our work are presented. Chile has 43 volcanoes which are distributed throughout the whole country. This causes a large number of volcanic activities which are monitored by the OBDAS, Volcanological Observatory of the Southern Andes. Here we can see an image from inside the observatory. The OBDAS is in charge of volcanic surveillance and non-forecasting explosion. They analyze signal capture from volcanoes to identify events. In this paper, we work with the Nevados del Chillán volcano, located 444 kilometers south of Santiago and 119 kilometers south of Talca. It's one of the country's most active volcanoes. The typical eruption style is explosive, with some notable events in 2016 and 2009 and 2003, 1986, 1973, among others. The main motivation of this work is to optimize the events detection to improve the automatic classification on continuum monitoring in order to obtain information about the volcano state. Monitoring a volcano is hear and see activity inside a volcano. Volcanic surveillance is based on the substantant movement of molten rock or magma peak. A volcano will occur before any eruption can start and can be performed by four methods principally: visual observation, growth deformation, chemical analysis, and seismic monitoring. In this work, we use the seismic monitoring using the network of OBDAS in order to have signals to detect and classify. Volcano events are principally three: long period, volcanotectonic, and tremor. These signals are present in this figure, and we are able to see some difference from one signal and another. The principal assumption used in this work is that the volcanic seismic signal can be represented by analytical monocomponent and nonlinear frequency modulated signal given by the following equation. Additionally, we assume that the analytical signal is disjoint in time and frequency. That means that the evolution in time do not affect the change in frequency. In this case, we have the analytical signal, the instantaneous amplitude, and the instantaneous phase. In order to obtain the instantaneous frequency, derive the phase. The instantaneous frequency is linearly decomposed of hyperbolic secant function, and the coefficient of the series is obtained from the inner product between the instantaneous frequency and the hyperbolic signals. Finally, we calculate the instantaneous phase and synthesize the original volcanic signal in order to calculate the spectrogram of the reconstructed signal. Additionally, we present the time-scale representation in the same form that a spectrogram. In this figure, we present a comparison applied to the LP, BT, and TR events. In the left, the short-time Fourier transform spectrogram is applied to the signal, and in the right, the hyperbolic secant time-scale transform Qerlet. for the same signal is presented. In this paper, we used the Visual Geometry Group (VGG) from Oxford as a convolutional neural network architecture with 16 layers and its use as vision model with excellent result. The input data correspond to an image of 224 by 224 by 3 of resolution, and in your case, we use the scale spectrum from a volcano seismic event segment in time. The architecture of the network consists of 5 convolutional layers. Layers 1 and 2 include 2 convolutional levels and 1 2D max pooling level. The layers 3, 4, and 5 consist of 3 convolutional levels and 1 2D max pooling level. The convolutional levels have a ReLU, rectified linear unit, kernel activation function of 3 by 3, with pulse size equal to 2 by 2 and stride 1. Finally, the output is transformed to a 25.088 by 1 vector, which is based to a full connect layer of 128 neurons adding a dropout of 0.2. Then the classification is performed by a full connect neuron layers equal to the number of classes. The initial weight in the 5 convolutional blocks were taken from a model already trained in the imagined set. In order to train the VDD16 layer, we use a set of data ranging from 2015 to 2017 with 4,893 LP events, 4,675 BT events, 2,517 TR events, and 3,472 OT events that correspond to 50,557 events in total. The training database is formed by events that are manually segmented, and their classification is provided by the expert of the OBDAS located in Temuco, Chile. The image for the convolutional network consists of spectrum calculated using equation 1 and adjusted to the 224 by 224 by 3 dimension to fit the VDD16 input. Although the events have different duration, they are all represented in 224 horizontal pixels. This is a kind of time normalization, while the frequency range, vertical pixel, is static between 2 and 25 Hz. A sample of 100 images per class used to train the VDD16 is presented in this figure for LP events, this figure for BT events and for TR events. VDD16 is trained with 50,557 events in total range from 2015 to 2017, with the 80% for training and 20% testing set. We obtain up to 75% of exactitude. In this work, the detection and classification steps are performed separately. Detection requires the segmentation of an event from the background noise in the seismogram. This implies detecting the onset and the end of the event. This is particularly important as it defines which signals are going to be classified and which are going to be discarded. The detection is performed by the well-known LTA-STA radio because it is a robust tool widely used by analysts to detect an event. The adjustment of the LTA-STA requires an amplitude threshold above which the incoming signal is considered a seismic event. This threshold is critical due to the fact that lower values give a high rate of detected events and higher values give a lower account of detected events. This figure shows the result of applying LTA-STA over the continuous signal of the October 10 of 2019 between 8:53 and 22nd and 15:40 signal of 5,180 sample lengths. For each detected event, we apply the BDD over the spectrum of the segment signal, and the Qerlet decomposition are used to classify it. The methodology is as follows. To evaluate the performance of our system, a blind set was taken from the continuous seismic signal from September 13 and September 19, 2020. From this blind set, the correct classification rate, false positive rate, and false negative rate were calculated. 3 amplitude threshold values were applied: 2 micrometers per second, 5 micrometers per second, and 10 micrometers per second. The result for these values are present in this figure. For each day, we compare the result of time from the system and the of the reference. From figure, it is possible to see the threshold define the false positive negative rate. In order to determine an optical threshold, we decide to acquire the area of false positive and negative. This occurs when threshold is equal to 3.295. Figures show the relation between estimated events per day and events detected in OBDAS. These parameters show that the threshold affects the amount of events per day, but the accumulative events in time remains with the same tendency. This is a very important aspect due to the fact that the 20% of overdetection of our system will have the same behavior tendency that the reference. In this paper, a method was proposed to optimize the LTA-STA performance based on a test dataset and using the trade-off between FP and FN to define the algorithm threshold. 2 classification methods were used to validate the proposal, and they show that the optimal threshold is more robust than the other manually defined, in particular from the Qerlet classifier. Total performance of the system depends on the amplitude threshold selection. This amplitude corresponds to a value that depends on the evolution of the seismic signal over time. Due to the inexistence of criteria to optimally set this value, we analyze different threshold values, starting from the recommendation of the OBDAS expert, but also testing other values. Finally, we propose a method to determine an optimal threshold when the false positive and false negative cure area are required. The optimal threshold implies an overdetection classification of the system, but this aspect is well considered by experts at OBDAS. Also, with this study, we conclude that high values of amplitude threshold give an underdetection, but in the same way, the overdetection, the temporal tendency of amount of events per day is the same. This is how the general trend of the number of events is protected. This tendency is useful when volcano behavior is studied by analysts, seismologists, and experts in order to integrate with other variables and chemical acoustic deformation, among others. Thank you very much.